All right, looks like they're trickling in. Keep on working till we get that turned in. Oh, there we go, about half the class. All right, let's go over that warm up. So the overalls, when you add all the equations together, kind of like Hess's law style, they're on opposite sides, you cancel. Get this a little more focused. Okay, so we should have, so chlorine cancels. And so you have two of them and two of them here, 1, 1. And then CCl3 also cancels. So you'll have diatomic chlorine, CHCl3 for your reactant, hydrochloric acid, and carbon tetrachloride as your other product. So that's your overall reaction. What were the intermediates? We had two. We have chlorine and CCl3. Those are both our intermediates. Now for the molecularity, that's only talking about, that's not the same as the order. This has to do with elementary steps. This one's uni, there's just one thing. Two things, so bimolecular, unimolecular, and bimolecular. And then our rate determining is our slowest step. So for this proposed mechanism, it's step 2. So when we read the rate law based off of that one, it would just be off the reactant. So Cl times CHCl3, that's this guy times K2. I put it in a funky order, so it'd be this. Well, we have an intermediate, right? Chlorine's an intermediate, so I'm gonna have to substitute. Now, the only one that's reversible on our homework, they were all reversible, but this is step 1 was the only reversible one for this one. So I set those rates equal to each other. K1 of diatomic chlorine equals K negative 1 of chlorine squared. Divide by K negative 1, divide by K negative 1. To undo the square, I square root. And my chlorine, square root is the same thing as raising to the 1/2. So now I could substitute this in for my intermediate. So I have chlorine to the 1/2 times K times CHCl3. The overall order would be 3/2. It didn't ask for that, but it gave you a hint like, hey, it's not an integer, it's going to be a fraction. Any questions on the warm-up? All right, then let's go over the homework. So some more mechanisms. So one we basically did together. Hold on, I gotta get this all. There we go, situated. So for A, for 1, here's my overall. I just wrote it, you didn't have to, but B is an intermediate. If step 1 was the rate determining, it's just rate times K times A. Great, no intermediate. But if step 2 is your intermediate, you get rate K2B, but B cannot show up because it's made here and consumed here. That's our definition of an intermediate. So I'm going to set this step 1 equal to each other. So K1 times A equals K negative 1 times B. Solve for B, divide by K, divide by K. So when I substitute back in, K2 times K1 over K negative 1 times A, which simplifies to rate equals K times A. Now the second one, same thing, the first step, if that was the slowest, great, no problem. But if it was step 2, sorry, I'm running out of room on my end, then we have an intermediate. B ends up being an intermediate again. No, I'm sorry, C. C is an intermediate. Made here, consumed here. So intermediate. So here's the rate law based off step 2, A times C. Great, but C can't show up because it is an intermediate. So I set the forward and the reverse rates equal to each other. So K1 times A equals K negative 1 times BC. I'm going to solve for C, divide by K negative 1B on both sides. And then it comes, and I substitute in K2 times K1 over K negative 1 times A over B. That becomes K, A squared over B. Questions on number 2? All right, then let's look at number 3. If the first one is a rate determining step, it's A squared. And since this is an elementary step and there's a mechanism, you can write the rate law based solely off of this. Now, before, when it was, you don't have a mechanism, you can't assume that, right? This was like that next layer. You have to have data from the lab. Okay, if this one is our rate determining step, C is an intermediate and it would show up C times D. So we can't do that. So we're going to set this one equal to each other. A squared BC, solve for C, divide by KB, substitute in K2 times K1 over K negative 1, A squared times D times B. And it becomes this. Don't forget to have rate equals and your K, no numbers. And then if there's no questions, let's go to back. All right, so here C is intermediate again. Rate law for if step 1 was the rate determining step. And then if it was step 2, C is an intermediate. So we have to solve, divide by K on both sides, substitute in, you get rate equals K AB. And then for the next one, this would be KA squared. If it's this one, B is an intermediate here. So we have to substitute for B. So KA squared equals KB, divide by K, substitute in, you get rate equals KA cubed. All right, any questions on those so far? Okay, then we got to a little bit of an application part. So this one said, all right, here's your overall reaction. Like if you add your mechanism up, you're gonna get this. 2A plus B gives you 2C. So that's the first step. You wanna propose some steps that add up to this. And then based off the slowest step, that you get to tell me what the slowest step is, you should get this as your rate law, A squared times B over C. Since you have a fraction, you know in your slow step, you need to make an intermediate. There's multiple correct answers. This is one that I have. I proposed, and you could have it in lots of steps. I did 2 steps. I did A plus B gives you C plus something else that's not in here. And then I made that an intermediate. I made it here and consumed it in step 2. And I got A plus D gives me C. So when I add this up, I'd get 2A, B, 2C. So that matches up, great. I made the second step my slow step, would be K times A times D. Well, D, I made an intermediate. So the first, if I set these equal, A times B times C times D, to solve for D, I divide by KC, I plug in, simplify that, I got that rate law. So this was my proposed mechanism with 2 steps, with this being my rate determining, but you needed an intermediate. Someone else, I think Chase in the other class, he did one, which was pretty similar. He did A plus A gives you CD, made D the intermediate like I did, however here, B plus D gives C. So then you still get 2C, 2A plus B. He had the second step B as intermediate. So if you substitute the 2A or A squared equals CD, divide both sides by KC and substitute in, you still get that same rate law. So this was another possible proposed mechanism. And then the last one, you could, I at first was like, oh, it's great, you can do that. It's the same, but I forgot you can't, having term molecular is super rare. So one proposed mechanism you could have had is A plus B gives you C, B plus C gives you D, having C be an intermediate. So you get A plus 2B gives you D. Make this the rate determining, so B times C, but then you have to substitute A, B gives you C, divide by K, then you would get this guy as well. And I'll post this key online after school today. So chapter 14 is all about rates and speed. Okay, so we first talked about what factors affect the rate. And you guys did your first lab that's due on Friday by 4 about that. You picked a factor, whether it's temperature, surface area, concentration. We also talked about catalyst, but that wasn't one of your choices. And what that does, right, is it increases the chance of collisions, and then that increases your chance of a successful collision. Correct amount of energy, so that's your activation energy, the right orientation. Then we learned about rate laws and the order, and that you have to have experimental data. Then we took the integral of those rate laws and brought in time-dependent rate laws. So you want to make sure you know how to use those, which ones for which order. And that's going to have to do heavily with our lab tomorrow, is we're going to determine the rate law using some data of the Crystal Violet lab, which I'll talk about that. And then the very last thing was mechanisms. Maybe it's multiple steps. So we're going to move on to chapter 15 today. So I am going to go to our PowerPoint. It is posted. And we're going to be talking more about equilibrium. So that whole when the rate of the forward is equal to the rate of the reverse. So that's why I kind of want to sum up chapter 14 before we move on. Our lab tomorrow is on rate laws, though. Alrighty. Okay, so chapter 15, chemical equilibrium. So equilibrium is when the rate of the forward reaction is just as fast as the rate of the reverse reaction. So in this one, we have N2O4. It's a solid. It looks like it's clear. And this is before the reactions happened. Now some time has passed. It started turning more like a rust color, which is what this NO2 is. This is like a rust, and this is clear. Clear, rust. Notice there's just one arrow. Here there's only reactants. Okay, it starts going, it's moving the forward, moving the forward, moving the forward. Now it's reached an equilibrium. It's a little bit darker. It's reached its happy spot where N2O4 is turning into NO2 just as fast as NO2 is turning back into N2O4. See these two little brown ones come together to make this, and this bond breaks to make these two. And they're happening just as fast at the same rate. And that's what chemical equilibrium is. And we show that by this little double half arrow. And that occurs when a reaction and its reverse proceed at the same rate. And it always reaches chemical equilibrium. That's the thing. So as a system, and notice there's no concentration on here. It's just rate, how fast it's going, and time. So as it approaches equilibrium, its happy spot where the forward's equal to the reverse, notice that's where these times are the same, right? There's the rate is the same. So here's the rate log constant for the forward. That's what that little F is. Rate log constant for the reverse. That's what that little R is. So as the system approaches equilibrium, both the forward and the reverse reactions, they're happening. It's not like one stops. Oops. And then they reach this equilibrium and the rates are equal. So at equilibrium, the forward and the reverse are proceeding at the same speed, the same rate. And I'll go back, hold on one second, which means they want to like emphasize it's not just, oh, it goes forward and stops. Oh, I didn't even mean to use the highlighter, but that's kind of cute. Okay, that means that this is breaking up just as fast as these are coming together. And it just keeps going, 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 going. And that's called dynamic equilibrium. Dynamic meaning like it's still moving. This is still moving forward and they're happening at the same speed. Doesn't mean the same quantity. Doesn't mean the same concentration. That's not what's on the axis here. Just that it's the same speed. The next graph, though, we're going to look at when we bring in concentration. Okay. So now concentration's on this axis. And so it says once equilibrium is achieved, which is right here for this one at this time or whatever, the amount is constant of each the product and the reactant. Notice they're not the same amount, but they haven't changed. So notice that means we've started with no rust color, but all clear. This looks like it must be a reactant because its concentration goes down. It's breaking down, making product, making product. This product amount is going up, makes sense. The reactant's going down, the product's going up. until they reach the same speed of breaking down and coming together, the forward and the reverse. And the amount of this and the amount of this are constant, which is not the same as the same, if that makes sense. Like this one's 10 molar and this is 5 molar, something like that. But it's going to continue to be 10 molar. And it's not going to be the same molecules. These are breaking down and these are coming together. It's just happening at the same rate. So you have a constant amount of each. So since in a system at equilibrium, both the forward and the reverse are being carried out, that's why we write the little double arrow to show it's an equilibrium. Okay, now we're going to see another K, but it's going to be derived from the little k's, the rate law. So remember, little k is from chapter 14. The units are very, very important. It's temperature dependent, and you can solve it when you have concentration and time data from an experiment. Okay, this is going to be important because we're going to move into the equilibrium constant, which is a big capital K with no units. This is section 15.2. So say you have this reaction. This is our the reaction from before, the clear and the rust. This would be your rate law. If I told you this was the elementary step, you would have the K of the forward times your reactant. Again, I was like, hey, this is an elementary step, what would the rate law be? And it was your slowest step. If I flip it and I do the reverse, the rate law, you don't have to write this on our next slide, would be Kr NO2 squared, right? If we did the reverse. That's what this is saying. And then what we learned, because we had to substitute in chapter 14, equilibrium means if our rate is based off of this for the reverse, and it's based off of K and 204 for the forward, and we said the rates are equal, we can now set those equal to each other, which we did before for our last worksheet for substitution. Right? The rate of the forward equal to the rate of the reverse. Here's your rate law for the forward, here's your rate law of the reverse, we set them equal to each other. If we rearrange this and get all the K's on one side, it becomes this. And this ratio of these guys, we just now call that an uppercase K, or the equilibrium constant. And it's always equal to your concentration of your products over your reactants at equilibrium. So when it reaches its happy place, when the forward reaction rate is equal to the reverse reaction rate, however much you have of your products over reactants, you can get something called your equilibrium constant. And we'll learn about this here in the next few slides on what that tells you. And it's an important ratio. So the ratio of the rate constants, our little k's, at the same temp becomes this. Your products over reactants is equal to your equilibrium constant. The little subscript EQ just is a general for equilibrium constant. It's a capital K. There are no units. We just want to see, is this number way bigger than 1 or way less than 1? Because that's going to tell us who do you have more of when it reaches its equilibrium. And our homework, we're going to be practicing writing the equilibrium expression. Just like the rate law has no numbers in it, just the chemical species and the variables, whenever I'm asking the equilibrium expression, no numbers, and you get points for that. Same with the AP test. So if you see expression, they just want something like this. So the expression is, say you have this reaction where your lowercase are your stoichiometric mole ratios. Your products, concentrations at equilibrium, are put over your reactant concentration at equilibrium. And then they're raised to whatever your mole ratio is in the balanced equation. So like rate law, you didn't even necessarily have to balance the equation, but in this you do, because that's the exponent that these are raised to in its equilibrium expression. So C just means it's the equilibrium expression in concentration units. It's like KEQ is like the big umbrella. It's products over reactants at equilibrium. And you could either do it in molarity, or we learned that we know that if for gases, the molarity or concentration is directly proportional to the pressure. So you can also express it in pressure units. And we'll see that on the next slide. So since pressure is proportional to concentration, you have a high pressure, that means you have a high concentration. You can also do products over reactants, but in pressure units. So if you have the pressure at equilibrium, you can substitute those in, and that's totally fine. Notice though, when they ask for expression, it's going to be different. If it's concentration, you need to show brackets. If it's pressure, it's capital P with the subscript, whatever gas, but still raised to your stoichiometric ratio. ATM, torr, MMHG, whatever, it's fine. And then your K does not have any units. Little k does, and they're very important. Big K, no units. And if you have enough stuff to do KP and ask for KC, that's fine. We have an equation that we can convert between the two or vice versa. And it's derived from the ideal gas law. So this is the relationship between KC and KP. We have our good old Pivnert. We rearrange to get moles over liters. Let you guys write that down. And you get this. This is how you convert KP into KC. This is our good old gas law constant that's on our AP sheet. This is temperature in Kelvin. And then that's raised to your change in moles. Change in moles are your moles of, notice it's just gases. Gas product minus gas reactant. So say I had gas A plus gas B yields gas AB. I'm going to totally make this up and put this, even though this doesn't balance. The change in moles here, since they're all gases, you do 3 minus, there's 1 mole here, 1 mole here, they're all gases, 2. So your delta N would be 1. If it was a solid plus B gas yields A B gas, it'd be 2 minus 1 would be your delta N. It's gases only, and it's products minus reactants, and that's what goes right here. And this will have on our 5th work. You won't need this for, I think, tonight's worksheet, but you will for the next one. Maybe you have enough to get KP, but it wants KC. You just plug into this equation and you can convert between the two, or vice versa. Okay. So now let's look at some data. So we did 4 experiments, and we either changed the, this is that same experiment where you have the clear and the rust color. This was, which one's rust? So N2O4, this is clear. And this one's rust, like an orangey rust. Okay, so experiment 1, we started with the rust color and let the reaction go. And we get this, our product over reactants is equal to this number. And this is the concentration at equilibrium you get of this one and of this one. This one's our clear rust. And we get K by putting our products over reactants. It's a ratio at equilibrium. All right, we did 3 experiments where we did the reaction in reverse. And we tripled it. No, I'm sorry, we doubled the amount of reactants. Or sorry, I guess we can call it reactants in reverse. We did it with 3 molar, 0.03 molar. And no matter what, the ratio of your products to reactants ended up being 0.2, 0.2, 0.2. Okay, what if we did the other way? We start with the clear one and didn't do this one. We still got a ratio of products to reactants of 0.2. So no matter where you start or with whatever concentrations, it's going to get to its happy place, which the chemistry word for that is equilibrium. It's always going to reach this product over reactant ratio. Each reaction has its own happy place, and this number tells you which one you have more of. And that's what we'll see on the next few slides. The K gives you information about what's favored at equilibrium. Because no matter what you start with, how much you start with, it's going to get there. As you can see, the ratio of this to this remains constant at this temperature, no matter what the initial concentrations are of these guys. So here's a graph of your concentration of the NO2, which I believe was the clear one. Not that it really matters, but yeah, this is the rust one. Okay. This is the rust color. So here's experiment 4, right? So this was like where we either started with the rust color or the clear color. So it's showing the difference between those two. So here, experiment 3, we start with the rust color. The amount went down until it reached its happy place. It's nice and constant. Or if we did the reverse reaction, started with no rust, it's ramping up, and then it stays constant. No matter which way you start, this data is from the last 2 trials. Oops, sorry. From the previous slide, and no matter which way you come from, it's going to reach equilibrium. And equilibrium doesn't mean the same concentrations. It means the rate is constant. And it's going to be the same ratio of products to reactants. And it's going to get there no matter what. So here's a different experiment. This is called the Haber process, and we'll see an important video on that clip, I should say. So say you have some hydrogen gas, some nitrogen gas. They react to make NH3. And it doesn't matter if you started with the reactants. Here's where the rates are the same. Notice the concentrations aren't the same, but they're constant. Or if you start with the products, see there's 0 reactants and products. This goes down. These are being made until they reach equilibrium. And it's going to stay that way. Yay, right? These go down, this goes up until it reaches equilibrium. Does not matter if we start with the N2 and the H2, or if we start with the NH3, forward or reverse, or how much you do. They will all have the same proportions of all 3 substances at equilibrium. And the forward will be combining just as fast as the reverse is decomposing. Questions so far about equilibrium? Okay. Now let's say, like, why do we care? So what does K tell us? So capital K, our equilibrium constant, if it's bigger than 1, this is just being dramatic. Like, why is there 2 greater than yours? Just if it's because they're not going to give you like 1.0001. It's going to be like 50 or 300 or 5. There's a pretty big range. But if it's over 1 and K is always equal to your concentration of products over your concentration of reactants at equilibrium, if K is equal to 1, that means your numerator is bigger. And for K, that always represents your products. So when it reaches its happy place, its equilibrium, which it's going to do no matter what, this reaction has more products, or it favors the forward reaction, or it favors the products, what we say, at equilibrium. It's going to reach equilibrium, and you're going to have more products that are going on at equilibrium. If your number is smaller than 1, that means your denominator is bigger. And your denominator for your K expression is reactant concentration at equilibrium. So that means your reactants are favored, or you have more reactants at equilibrium. We just saw it as like the reverse reaction happens, or the forward reaction happens. And in sophomore year, we just thought, oh, we did that and it stops. Now you guys are more advanced in your chemistry. So it's not really that it stops. Both reactions are happening just as fast. You just get more product or more reactant when it reaches its happy place. And so the homework is you'll be writing your K expression, products over reactants, plugging in the stuff at equilibrium, and talking about our products or reactants favored. Something you'll see in your sample problems, there's a sample problem where you have to rearrange these things kind of like Hess's law style. And if you need to flip or reverse a reaction, in Hess's law, like that was when you had like reaction 1, reaction 2, right? You had your delta H, and whatever you did to this to get your overall, you did to the delta H. So if you flipped a reaction, you flip the sign of the delta H, and then you added them together. For the Ks, in the way their relationship works, if you flip it, you do the reciprocal. You flip, instead of the sign, you flip what's the numerator and denominator. And instead of adding your Ks or your delta H's, you multiply them. So it's just like a different type of problem. You can do like a state function where they give you the Ks of these different like elementary reactions, and you can get the overall K by combining the reaction, kind of Hess's law style, but the mathematical relationship's different. Instead of adding, like we add delta H, we multiply your Ks. Instead of flipping the sign, if you flip the reaction, we do the reciprocal of the K. And if you multiply something by 2, instead of multiplying the K by 2, you raise it to the power. So for this one, we raise this to the power of 2. Okay, we need to multiply everything by 2 to get things to cancel. So this is now raised to the power of 2. And you'll see that in your book on sample problem 15.5. When you get to that section, you'll be working on these slides. Okay. So it's saying like, hey, the equilibrium constant for a net reaction, just like enthalpy, is made up of 2 or more steps. Great. Is the product of the individual steps. So instead of adding them, you're going to multiply them. Okay, last section we need to get through so you can do your worksheet is your states of matter. So the heterogeneous equilibrium. So if you don't have all gases or all solids or whatever, what goes in there? So liquids and solids, if they're there, they're good to go. They're constant. They're not going to go in your equilibrium expression. So you omit liquids and solids from your equilibrium expression. This says both can be obtained by multiplying the density of the substance by its molar mass. Great. And both of these constants are constant temperature. You don't get more or less liquid as the temperature change. You don't get more or less solid as the temperature change. But with aqueous, which is how much dissolves or not, or with gas, you do. So those are the only states of matter that go in your equilibrium expression. And that's what it's saying. So therefore, the concentration of solids and liquids do not appear in the equilibrium expression. So let's say I said, hey, write the equilibrium expression for this. It'd be K equals the concentration of Pb2 plus, it's the ion, not the solid lead. So you need to make sure, it's brackets, times chlorine squared over 1, because solids are omitted. If this was a gas, then it would be over PbCl2 gas, or if it was aqueous. Let's say this was gas and this was a solid, then it would be Cl squared over PbCl2. So solids and liquids are omitted. If these were both like a solid and a liquid, then it would just be 1 over PbCl2 equals K. So aqueous and gases only go into Kc. Kp, gases only. So that's important to know. So in your equilibrium expression, gases and aqueous go into Kc, your products of reactants, gases only into your Kp. Oh, there it is right there. So here's like calcium carbonate doing a decomposition reaction. You always get CO2 gas and a metal oxide. Calcium's a metal. As long as you have some calcium carb and calcium oxide, right? Solid. It's going to happen no matter what. It's still going to reach equilibrium. It's all good to go. Those concentrations aren't going to change. If I were to write the Kc for this, it would just be CO2, right? Products over reactants, but these are solids and they're omitted. If it was Kp, it would be written like that. If this was a solid, then you would say your Ks are undefined. Any questions on that? I know we're running out of time here. Okay, so your homework for tonight, of course, outline, surprise, surprise. We'll talk about ice tables next class. This is due Friday. One-sided worksheet. Go, go, go. Come on. You have 3 problems. Here's a reaction. Balance it. Write your Kp expression. Remember, that's no numbers, just the expression. And write your Kc expression. Same here. Here they give you some stuff to put in. So you're going to do your expression and then plug in these values. The only values that can go in are either gas, like ATM, things like that. Or if it's Kc, it's molarity, moles over liters. So make sure you divide these first. Put them in a molarity before you plug it in your K expression. Okay, the last thing I want to talk about was our lab really quick. So lab is tomorrow. So you either come to session 1, session 2, bring goggles, bring something to write with. I'll have the lab printed out. So when you come in, go by that table, grab it, head on upstairs. And make sure you have a flash drive. Either you or your partner have a flash drive. because one of the sets of data is a lot. You don't want to write it all down. And it'll be easier when we do the Excel. We learn how to mess with the numbers in Excel. So you're going to come in, you're going to make some concentrations of crystal violet. Our stock solution is 25 micromolar. This is what crystal violet, the stock solution, looks like. It's really pretty. It's purple. And our pre-lab, you're going to bring that. I think question like 3 or something like that asks you, hey, how are you going to make, give me like 30 seconds. So make sure you bring your pre-lab. And here it tells you, okay, how would you make these concentrations? Here's your stock, and I want 10 mils of each, right? That's our good old M1, V1, M2, V2. Here's our M2. What's our V2? How much water would we put in? This is how much I want to make. This is the concentration. And that's your rate determining step for these, right? Is making your different concentrations. So you'll have a test tube rack, test tubes, you have your stock, you'll have your pipettes, mark them up. Then you're going to calibrate your colorimeter at the correct wavelength with DI water. Kim White, put it in the correct way, take your concentration, get the absorbance. Pour it out, rinse it out, next one. Absorbance. Okay, then we'll have our nice calibration curve. Then you're going to take just the stock. Like remember before it was the Gatorade we just put in there and got one number. Great. Or we took the bullet solution, put it in, got one number. Great. Okay, for this one, we're doing a chemical change. So we're going to take our crystal violet and add some base. And over time, it gets less purple. I'll just sit for a little bit. And so we'll put our crystal violet, put some sodium hydroxide, cap it, and then we'll set up the LabQuest to take absorbance like every 5 seconds for like 10 minutes. Then when it's done, we'll stick in our flash drive, drag all those numbers onto the flash drive. And then in class, I'll show you how to manipulate, because then we're going to change all those absorbances into concentration using our calibration curve. And I'll show you how to do that in Excel. Then you're going to graph concentration and time, see if it's zero order, concentration and the natural log. Nope, I'm sorry. Natural log, concentration, and time. And I'll show you how to do that in Excel. So you have to do like each number. Highlight, add a graph, look at your R squared, see if it's first order. It's getting lighter, you can see. And then we'll do 1 over the concentrations versus time and see if it's second order R squared, and that's the lab. And then once you know the order from their Y equals MX plus B, you can get the slope and then get the K constant, the little K back from chapter 14. All right, it's a little bit lighter than our stock, you can kind of see, but it's going to fade over time. And so our colorimeter is just going to take absorbance, and then we're going to end time. And yeah, so main thing, bring a flash drive, bring your pre-lab, bring a mask, something to write with. I'll see you tomorrow. Thanks for hanging out those 2 extra minutes. I appreciate it. I'll see you then. Bye.